perturbation theory for the free energy, when the free energy functional is ddx m square by 2 phi square plus half grad phi square plus lambda over 454. And the thing which the partition function would be z, which is the functional integral over e to the power minus f. The correlation function would be, let's say, some c x12 would be notation wise the expectation value of phi x1 phi x2, which is equal to the functional integral phi x1 phi x2 e to the power minus f divided by z. The practical thing is to do the calculation in Fourier space or momentum space, what have you, whichever you want to call it. So Fourier space, which is the wave number, has the measure for this d phi, a practical quantity, which is d phi k for all k and minus k. So this essentially, or let's put the minus on as well. So it's the all possible values of k with and similarly with the minus k, and this is the measure, which is this. And in the f in Fourier space looks like d dk, and then is m squared by 2 phi k phi minus k plus half k squared phi k phi minus k plus lambda over 4 phi p1 phi p2 phi p3 phi minus p3, and here there is the integral over p1 p3. So that's the setup. And where we were is that we were calculating this z over here, and we were z, which is now d phi k. So this is in the measure in Fourier space, and here is integral d dk and m square by 2 plus k square by 2 phi k phi minus k. And the other part was the difficult, the only, I mean, the can only do Gaussian integrals. So that is the technical constraint. The only integral, functional integral one knows how to do is Gaussian integrals, and therefore that is what you need to reduce things to. And so it is one, that is Gaussian integrals, meaning this e to the power whatever has to be just x squared. You can have e to the power minus x square, x into e to the power x square. That's all still the family of Gaussians. What I can't afford to have is evaluate an integral with this chap sitting in the, which is another way of saying the simple thing that e to the power minus x squared dx you know how to do, but integral e to the power minus x4 dx is not something that you can do. So it's as simple as that. I mean, I can't do it with one variable. I can't do it with an infinite number of variables, period. So it is 1 minus lambda over 4, and then it is phi p1, phi p2, phi p3, phi minus p1 minus p2 minus p3 times the differentials d phi p. Oh no, that's already there, so I don't need to. All right, plus lambda over 4 square half, and then integral distance. So that's it. That's what we were, and it is up the so what we said was that, look, all right, I know what the first term is. The first term is pi over k, pi of k, 1 over k square plus m square root of half. That is this first term over here. And now the point was that I need to do the other terms, and this we wrote down. So minus lambda over 4, and I have this functional integral part, which is d phi and e to the power minus whatever, and then there is the integral p1, p2, p3, and with this won't write, and then is so that's the first term. The next term would be half and this. And for this first term over here, what we did was, well, number one, I mean, one takes out this and bring that's but the question of doing this one over here, the way one does it is to put draw a diagram, that is, because this thing is going to be become the only time the integral will exist if this exists, which is non-zero, if p1 equal to minus p2 or minus p3 or minus p2 minus p3. So p1 has to be either minus of this, so that you have phi p1, phi minus p1, and then the other is phi p3, and p2 has become minus p1, so this becomes automatically phi minus p3. So you can factor this. This is one correlator, this is the other correlator, and that is when it is non-zero. If none of them, if this pairing does not happen, if all of them are different from each other, then you are looking at averages of phi p1 times phi p2 phi p3, and that is not going to, that is 0. So the only option, non-zero option left for you is to pair them, and if you pair them, then automatically, I mean, this has to become this and this has to become this. And if that is going to, so I know what this is, that is 1 over P1 square plus M square. This is also 1 over P1, this is 1 over P3 square plus M square. So you have this over here. It is 1 over P3 square, P1 square plus M square, provided all the others are cancelled out, and that cancelling out of all others means that I take this out of it, and what I'm considering when I write down this as, when I write this down as 1 over P1 square plus M square, what I'm saying is that I'm actually calculating, integral d phi phi p1, phi p2, phi p3, phi minus p1 minus p2 minus 3 e to the power minus ddk, let's say 2 pi to the power d phi k phi minus k square plus M square, divided by integral d phi e to the power minus that quantity over here. That is the quantity which is 1 over that is the quantity which is 1 over P1 square plus M square into 1 over P3 square plus M square. Unless I divide out by this one, all the other things which were there would not cancel out. So it is essentially, I have factored this out, and this is in the denominator of all the integrals, and therefore, except for those which appear over here, all the others cancel from top and bottom. So that's that. And then when we were doing these integrals, if I have 2 of them divided by this, then the answer is 1 over P1 square plus M square. So that's that. All right. So this we said we will adopt a shorthand that the shorthand is that I look at, so I draw the first I draw make some notations. This is a vertex, and there are 4 lines in the vertex because there are 4 phi's over here. Each line effectively is like a phi. So this is like phi p1, phi p2, phi p3, and phi minus p1 minus p2. So that I have a vertex. I have a line which is not to be confused with a line coming out of the vertex, which is just phi p. I have a line which stands by, when it's a line which stands by itself, it is a propagator, which is 1 over p squared plus M squared. That is what a line by itself is. So I have a vertex, I have a line, and then I have to look at this chap over here, which is 1. I mean, you start with a 1 minus this quantity divided by that in the denominator. So now I'm in business. I have a 1 which comes from this part over here, which is taken out, and a 1 kept inside with the, it is the, so it's factored out and 1. minus one interaction brings me a lambda over 4. So lambda over 4 is the vertex strength, so that is the interaction. So now the interaction, the vertex is given by this quantity over here. And there is nothing else. So since there is nothing else, what you have is you have to connect. To get a non-zero thing out of this, I have to actually connect and do this over here. So that is the answer. But I could have connected in 3 ways, right? I have these 4 lines, 1, 2, 3, 4. I could connect 1 and 2, 3 and 4. I could connect 1 and 3, 2 and 4, or I could do 1 and 4 and 2 and 3. So that is the combinatorial factor 3, which comes from my saying that this pairing can be done in 3 different ways. P1 goes with P2 and so if I did not go through that language, I could just draw this picture over here and count how many ways in which I could draw a closed figure. And that would give me the factor of 3. And and what's the analytic expression for this picture over here? Well, the analytic, so this thing closing on itself is, this is a momentum P, so it is 1 over P square plus M square. And you have to sum over, as it closes on itself, you sum over all P, and there is a ddP and a 2 pi. Whenever there is a ddP, there is a 2 pi to the power d. So this chap is this integral over here, this closed single loop is this 1 over P square plus M square, and you have to integrate over it. So this one will translate into, this chap translates into 2 of these, which is a square over here. So that's our way of going about it. If I come to the next part, then you see the next time around, I have 2 vertices in this. 2 vertices, and they have to connect in different, there cannot be any external legs. They will all 4 have to correlate with all 4. So I can do, I mean, they can do that internally, they can do with each other. One possibility is simply to have this over here. And this, you see, this does, what would be the weight factor? This you can do in 3 ways. This you can do in 3 ways. For every one over here, there is 3 over here. So that is 3 into 3. That would be the weight factor. Then there would be the kind where you can have this, and this chap over here. So this rabbit. So and now similarly, I would have to count weight factors, that I take this particular, I mean, out of these, I choose any two, and out of these, I choose any two, and they have to connect. So that would be the combinatorics for this, that choose any two out of this. So 4C2, another 4C2, and now you can connect those. So that's, and then there is the which you can do, I mean, pick any one of these and you can connect it in 4 different ways, and then you pick another which can go in 3 different ways, and then 2 different ways. And so here are, so you don't need to do anything else. I mean, this is the answer, that you have a have these diagrams for which you can write down integrals. The integral for this chap over here is this squared piece over here. If you have this one over here, if this loop momentum is P and this loop momentum is Q, then this loop momentum is P plus Q. Yeah. So it is, I mean, you write down 1 over P squared plus M squared, 1 over Q squared plus M squared, 1 over P plus Q whole square plus M squared. For square for this, I mean, there are 2 of them, and you integrate over P and Q. So that, and over here, it is P, Q, R, and minus P, minus Q, minus R. Yeah. So you write down 4 propagators and you integrate over PQR. So PQR. Huh? So and you put in the weight factors, you have it all. So what I'm driving at, that once you have got the picture, there, apart from doing integrals, there is not very much left. The integrals are a pain, but all right. I mean, worst comes to worst, you have to do a numerical job, but yeah. All right. So this sets the next important thing is the physical thing. I mean, look, I mean, this is not a physical quantity, but it exists everywhere. I mean, you cannot discard it. But on the other hand, it is neither, I mean, this does not correspond to anything physical. Which, I mean, all right. The point is that it is the free energy, if you take a log of Z, but one hardly ever proceeds in this manner. So the next vital thing is the correlator phi x1, phi x2, or the more conveniently one does it in momentum space and then takes a Fourier transform. So it is phi p, phi minus. So having known this business, I now don't, what I do is, I don't do any work, I draw a phi p line. So I draw a phi p line and wait, I put one interaction down, I do this, and I draw another phi p line. So there is a phi p line and a minus phi p line. There is a 0th order answer, which is 1 over p square plus m square. No interaction, this is the answer, which we know. Now I put a interaction down. So this is the 0th order phi minus p, which is this over here. And now there is expansion. I have written down the lambda over 4. So I'm imagining taking that free energy and expanding. So I have a minus lambda over 4, and then you have this phi p, and then you have phi k1, k2, k3, phi minus k1, minus k2, minus k3. And there is a lambda over 4, which I have written over here. And I have to consider the expectation value of this over here. All right, what? I can take this phi p. So this is my external line p, and here is my k1, k2, k3, k4. I can take p and join to any one of those, right? And so I can do that in 4 different ways. Because it is phi p1, phi p2, e to the power minus k square plus m square, phi k, phi minus k, sum over k, minus lambda by 4, and then with these sum over sums, phi k1, phi k2, phi k3, phi of minus k1, minus k2, minus k3. Now, this is to be in order to evaluate it, I have to write this. Only thing I can do is Gaussian integrals. So I do this, phi minus k, and 1 minus lambda 4, and then it is phi k1, phi k2, phi k3, phi minus k1, minus k2, minus k. So the first term is just phi minus p, which is the Gaussian integral over here. So if you if you take this out over here, I mean multiply through, that is first term is simply phi p1, phi p2, e to the power minus this thing. Next term is minus lambda by 4, and then it is phi p1, phi p2, phi k1, phi k2, phi k3, phi minus k1, minus k2, minus k3, and then it is e to the power minus the Gaussian. Isn't it? So this term is 1 over p square plus m square. But mind you, it is 1 over p square plus m square only when I have the z in the denominator. So when I'm saying that this is this phi p1, phi p2, this, and integral over the d phi, I have tacitly, said this is the expectation value of phi p1, phi p2, but there is, expectation value means that I have the z in the denominator. Like any other stat-mech expectation value, there is always the z in the denominator. Yeah. So I have 1 over p minus lambda by 4, which came from there. And now I'm looking at this. So what can it do? It has to close. So if it has to close, this can go and couple with any P goes and couples with any one of them. So it goes, let's say, and couples with K1. But there are 4 such possibilities. It could have gone to K1, K2, K3, K4. And then the other chap now has only has 3 options left to it. So for every 4 over there, it can go to 3. Once this P has picked up, this is the minus P. Once P has picked up any one of these K1, K2, K3, K4, then minus P's choice is reduced to 3. So for 4 times 3. Yeah. And then you have this integral. There is a 1 over P square plus M square from here. There is a 1 over P square plus M square from here. And this is integral 1 over K square plus M square ddk over 2 pi d. Whenever there is a loop, there is an integral. Open line is just the propagator 1 over P square plus M square. But then I could have done the other thing. So I have gone here, but I could have gone phi p, phi minus p. So phi p could have connected to phi minus p, and then I would have this over here. So there are 2 kinds of diagrams at this stage. There is this diagram whose contribution is this. So it is 1 over P square plus M square minus 3 lambda by P square plus M square whole square into ddk over K square plus M square whole square divided by 2 pi to the power d. And then there is minus and your lambda by 4, and I have P square, 1 over P square plus M square times this loop could have been formed in 3 different ways. So I just draw this loop over here. So that completes the top line. But then there is the bottom line, which is the Z. The bottom line, which is the Z, is 1 minus the lambda over 4 times this, which we have just seen. All right. So when you divide, it is 1 over, if I look at the top, it is 1 over P square plus M square into 1 minus lambda by 4 into this divided by 1 minus 4 lambda by this. So they cancel out. And you are left with minus 3 lambda by P square plus M square whole square, and this integral over here ddk over 2 pi d over 1 plus P square k square This whole square is wrong. No? It's just one loop. So k square plus m square divided by 1 minus lambda by 4 this. Right? So the answer is 1 over p square plus m square minus 3 lambda. So this minus this. So that combination cancels the 1 minus. So it is 1 minus 3 lambda into this divided by 1 minus this. But perturbation theory, this chap is to be dropped because it's this contribution, if I take it to the numerator, is lambda square. So that is important, but only when you go to order lambda square. In order lambda square, if you don't remember that you had this term over here, you will find no cancellation of disconnected diagrams. এই অবধি ঠিক আছে তো? এবার আমি পার্টারবেশন থিওরি করছি, সো এটা ডিনোমিনেটরে থাকতে পারে না, ওকে নিউমারেটরে নিয়ে আসতে হবে টু গেট দ্য ল্যামডা পুরো। সো নিয়ে এলে পরে এইটা যে সে তার কন্ট্রিবিউশন ইজ ল্যামডা স্কোয়ার। সো ফার্স্ট অর্ডার ল্যামডা যদি আমি কাজ করি তাহলে ওইটাকে আমি নেব না অ্যাট ফার্স্ট অর্ডার ইন ল্যামডা, কিন্তু ওটাকে নেব না সেটা কিন্তু নয়, কারণ এ একটা আমাকে ডিসকানেক্টেড গ্রাফ অফ সাম কাইন্ড দিল অ্যাট অর্ডার ল্যামডা স্কোয়ার। সো আমি যখন ল্যামডা স্কোয়ারের গ্রাফগুলো ওই ফাই পি ফাই মাইনাস পি থেকে আঁকবো, তখন যদি এইটা যে ওয়ান লুপ থেকে এই ল্যামডা স্কোয়ার উত্তরটা এসেছিল সেটা যদি মনে না রাখি, তাহলে পরে ইউল ফাইন্ড যে ওখানে দ্য ডিসকানেক্টেড ডায়াগ্রাম ক্যান্সেল করতে পারছো না। বুঝলে না? সো ইট ইজ নট যে এটা বেকার, ইটস ভাইটাল, কিন্তু অ্যাট দ্য নেক্সট অর্ডার। এই অর্ডারে যখন আমি অনলি দেখছি তখন এটার কাজ নেই। And therefore the first order answer is simply etar one over p square minus m square minus 3 lambda over p square plus m square whole square integral ddp ddk 2 pi. So the correlator, which is what? So phi p phi minus p up to order this is going to be done. ঠিক আছে? And that is the complete answer. So this is for what it's worth, the p equal to 0 করলে susceptibility পাবে। True, yes, p equal to 0, yeah, right, absolutely. All right, since you brought it up, as he said, P equal to 0 gives me the susceptibility. And remember that m squared is proportional to T minus Tc. It's some constant times T minus Tc. That was the. So P equal to 0. So this is, it is 1 over m squared. So 1 over T minus Tc. That is the Gaussian model answer, and susceptibility diverges as T minus Tc to the power minus 1. Come here, for d greater than 2, it's a divergent integral. So therefore, this perturbation theory makes no sense. I've done a perturbation theory, it's absolutely correct. There is no way in which there has been any error in this calculation, but it's a useless perturbation theory as it stands. It's good that you brought up this at this stage. If I set P equal to 0, I should be getting a physical quantity, which is the susceptibility. You calculate the physical quantity, perfect. The Gaussian answer agrees with the mean field answer. But then you look at this part, the answer is infinitely big. So you have, I mean, that is the warning. That was the reason why critical field theory was well understood. This is all standard field theory, but field theory was not an answer to the critical phenomena problem. So standard field theory as done in particle physics had no connection, it would seem, with the field, with the stat-mech problem, where my interest is in P equal to 0. The problem is that high energy physics, you are in the QFT class, you are doing the same thing, but it's all large P. And you can make sense of these corrections and so on, talk about them sensibly with renormalization scheme. Obviously that integral, that it's a divergence has to be there, but you define mass renormalizations to take into account these facts. I mean, you go with the inverse, it's P square plus m square minus this quantity, diverges, but you are not worried because the mass is to be renormalized. This is the bare mass, and the bare mass, which is infinitely big, picks up this infinite quantity over here and becomes the renormalized mass of the theory. And if your theory is good, then at the next order, it should prevail. So that's the whole idea of renormalization in high energy physics, as understood till the 70s. And you do that over. My interest is in this set of problems at P equal to 0. And I am really stuck.
Diverges for D greater than 2
2.
or D?
Greater than 2.
So for D is equal to 2, it should give a...
D equal to 2. D equal to 2 is the Ising model, which it won't give any.
But it will not be the answer as...
None. But the D equal to 2, it has it still has a divergence, it's log. So that it is not divergence free. It is only less than D. So what will it tell you? It will tell you that there is a phase transition in D equal to 1, where it is finite. So it's all rubbish. So below D equal to 2, it's rubbish. D greater than equal to 2 is sort of d greater than 2, d equal to 2 is a marginal case where, I mean, there are the logs which you have. So, all right. It's the propagator. Now, then, all right, what I was going to do, tell you what the, over here, we went to the next order. Now that I know how to do the diagrammatics, I should be able to calculate also what the next thing, not calculate, but write down, understand what graphs enter at the next order, right? So at this order over here, I know what has happened. There is the 0th order, and then there is this one over here. So next time around, your 12 combinatorics chilo 12, so 3 lambda by 4 chilo, or combinatorial factor to 12 chilo. এটা কি 9 হওয়া উচিত ছিল, or did I? ঠিক আছে। So I have 2 of these, and I have a line coming here, and I have a line coming here. ঠিক আছে? So, all right, first time around, you say, acha, I join this to one line, so this becomes a propagator. So this was just a phi line connected with one phi line, and it is a propagator with a 1 over k square plus m square 1 over p. And I have 3 chaps, and then over each vertex, as they see, can have now there's other, and you say I have these 3. So now you can connect each one, and you get a correlator here, a correlator here. So that's so that's the Shatai contributor. Now I could say, look, I join this, and then do this, and have one coming out, and do this, and this come out. Right? So there is this. This is not new. It is the geometric series formed out of that. So this is simply telling you that there will be diagrams of this kind on at all orders, and they will have a geometric, they will sum according to a geometric series. Yeah, for that, I mean, the combinator, you have to do the combinatorics and make sure that that has the geometric series, but it does happen. So this is there. Then it could be that all right, then I could go from here to I could go here to here and here to here. So I have this going this going from here to here, and you pick up this, and this comes from here to here and gives you, and then you have this. Huh. So there is this class that you have, and you similarly could connect from here to here, and this to that, and you pick up. So all the combinatorics has to be right. There are many ways in which you can do this. Huh? Then you can do you go here to there, and I have to have, yeah, you go, but all right, I can bypass. I go from here to here, and I can do the double plus all the others which we did. Right? So I can have all the others which I have done, and I can have this, and I can. So now what? Now look at all the disconnected chaps. When I do the denominator, that is the z, and expand, z has this, this, and this, right, at order lambda square. So this has this will this set is going to go away. And there should have been the 4. Right, no. So this whole thing, we can easily see that they go away because those are the which connects with. Now, what about this? This also goes away because that is the connector between the between this diagram over here and the denominator that I had over here, which I threw away. Remember, when I did the one loop, I said there is one term which is going to be like lambda square, and I'm throwing it away. There was this lambda times this one over here, which was divided by 1 minus lambda 4 times times something which looked right. And I said that I'm not considering now. But then in the which I had laid held out over there, that comes over here and cancels the. All right. So all disconnected gone. This is how loop by loop or order by order disconnected graphs cancel. তারা lambda square partition function দিয়ে cancelled হলো, আর a lambda order partition function যেটা বাকি ছিল ওখানে তার lambda square ঠিক আছে না? So এই মানে so all মানে ওই paperwork essentially taken care of. Yeah. And so you are left with, at the second order, so perturbation theory for G is which is the propagator phi is this, the zeroth order propagator, 1 over, and then plus, or rather minus lambda by 4 combinatoric factor into this. Then comes this plus lambda by 4 squared, that's just the and a half, which comes exponential is being expanded, so that is that. And then comes two of them, comes this, all right. All of the, if I call this G0, then this has the structure, this is equal to G0 minus coupling constant, which is over here. So if I include the coupling constant with this lambda by 4 with this chap, it is G0, this loop over here is sigma, and then plus, let's call it sigma 1, plus, then this is going to be this is G0, 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 right? So that is G0, G0, G0. So it is sigma 1, right? I mean, this is sigma 1, sigma 1, G0, sigma 1, G0, sigma 1, G0. And but this one is G0 sigma 2 G0. Huh? কি করে দিচ্ছি? No, the numerical factors, they are included in the sigma 1. The sigma 1 carries the sigma 1 is lambda by 4 into this. Huh? So and sigma 2 is half into lambda by 4 square into 2 of these. Huh? Combinatorial factors are included in the diagram. In how many ways I can form the diagram? Sigma 1, sigma 2, they have to carry the combinatorial factors. This is just the coupling constant. This is just the coupling constant, which is coupling constant is lambda by 4. So coupling constant can be taken out. Apart from the coupling constant, everything else is a combinatorial factor. So combinatorial factor goes into the sigma.
Combinatorial factor is lambda square and lambda cube with different.
Sure.
So
but they are by definition in sigma 1. মানে সিগমা 1টা আমাকে বার করতে গেলে আমাকে এইটা এই লুপটার কম্বিনেটোরিয়াল, দ্যাট ইজ যে এ যখন এসে ফাই 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 এইটা যে কত রকম ভাবে এই লুপটাকে তৈরি করতে পারে, which is essentially 3 into 2. So that 6 divided by the 2 that one had somewhere or other. No, that 6 is that 6 is the answer. When this combining with any 3, and that goes with this over here. Lambda by 4 is sitting outside. That is the coupling constant. But 6 is the property of this chap. Similarly, for every one of these diagrams, there is এগুলোর যা combinatorial factor হবে, you have to prove যে they are in a GP series. This and what you get in the all diagrams which are genuine contributors to this over here, but can be cut into separate parts by drawing a line, are reducible. And the reducibles would have to be such that they just form you see, it is G0 sigma 1 G0, G0 sigma 1 G0 sigma 1 G0. Eta hotei hobe. There has to be a GP series of this kind with sigma 1. At every order you go, this is order lambda square, this is order lambda, this is order lambda square. If I go to lambda cube, there will be G0 sigma 1, G0 sigma 1, G0 sigma 1, G0. Then there will be a disconnected, which is this with 1 sigma 1. At the next order, there will be G0 sigma 2, G0 sigma 1, G0. And then there will be G0 sigma 3 G0. So at every order, there will be diagrams which are a combination of reducible and irreducible. Reducible is when I can draw an imaginary line and disconnect the two. And every reducible is a GP series. So every reducible is a GP series. So therefore, the whole thing is that if it is it is going to be a GP series in sigma 1 plus sigma 2 plus sigma 3 and so on. The GP series always sums. G is equal to G0 minus G0 sigma 1 G0 plus G0 sigma 1 G0 sigma 1 G0 and so on. So that is going to sum so that I mean it is G0, then you add sigma 1 G0. It is G0 and then you add sigma 1 G0 square. So that's the sigma G1 G0 is the common ratio. So it is like saying G is equal to G0 1 minus sigma 1 G0. So G inverse is G0 inverse minus sigma. And this happens just as it happens for sigma 1. It also the same thing happens for sigma 2, same for sigma 3 and so on. And therefore it is you calculate the self-energy, the so-called self-energy, which means that you draw all the irreducible diagrams and the part of the irreducible diagram which you get by cutting out the two legs. That is the self-energy. and that self energy gives you the propagator, or correlator as G, which is the full G, as G inverse equal to G0 inverse minus sigma. Get the that is the whole story of perturbation theory. Whatever the subject, that is the perturbation theory. Does not matter whether it is classical physics, quantum physics, first order time development, classical physics, nothing doing. Everything has the same structure. হতেই হবে না, কারণ the sigma here is sigma 1 plus sigma 2. আরেকটা মানে the G inverse is G0 inverse minus sigma, and sigma is a sum, it is lambda times sigma 1 plus lambda square, sigma 2 plus lambda cube, sigma 3, and so on. Each at every order lambda, this is the irreducible diagram as self energy which cannot be cut. So first order, it is this. Second order, it is this. And similarly, the third order, whatever the thing is, you construct that. Now you have, when you expand, G is this, which means that G is G0 plus G0 sigma G0 over here, then that sigma has everything in it. So that sigma has everything in it. It means that everything is, what you have summed is G0 plus G0 sigma plus G0 sigma, G0 sigma 0, G0, and so on. That is what you have summed to write G inverse is equal to G0 inverse minus sigma. And this sigma you have over here, you can have just sigma 1. And then at this order over here, so this is G0 sigma, there is a part of it which is G0 sigma 1 G0, and then there is a part of it which is G0 sigma, let's say sigma 2 G0. When you come over here, there is a part which is G0 sigma 1 G0 sigma 2 G0, apart from having both sigma 1 and both sigma 2. Get it? So ওরা সবাই আছে। Yeah, ঠিক আছে? So এই হচ্ছে খেলা। This has a technical, this is known as Dyson's equation. The combining, just sort of formalizing the Feynman graphs. Dyson came up with this, the fact that what Feynman had produced in a diagrammatic series can be summed up and written in that cute form. And subsequently, the important thing is that every diagrammatic perturbation theory has this structure, no matter what the subject. It can be high energy physics, it can be many body condensed matter, it can be statistical physics, it can be equilibrium statistical physics, non-equilibrium statistical physics, everywhere the same thing. infinite series. Infinite series. Sure. Nishchay. So we are armed with this, and now I know that I am doing this 5-4 theory. The interaction is this over here, and G inverse is G0 inverse minus sigma at the order lambda, first order in lambda. I have just one, I mean, if I cut out the external legs, then the sigma is simply sigma 1 is this. And if I go to second order in lambda, after I have cut out the external legs, there is just the Shatai diagram, which and the story goes on. So but the point, unfortunately, is that what we have done over here, we have got this G. So go back to what we were doing. I have this G turn out to be 1 over k square plus m square minus 1 over k square plus m square integral ddp over p square plus m square 1 over k square plus m square. So that if I'm looking at this G inverse, then it is G0 inverse, which is this minus sigma. So it is this is equal to k square plus m square minus sigma, which is the function of m, right? So this will be a. So as was when we were doing this, and in response to this question, what am I? It is if I'm looking at k equal to G inverse k equal to 0 is the inverse susceptibility, because G is 1 over k square plus m square, and so all right. So this is the correlator. G is the correlator, and correlator is the susceptibility. So this is the inverse susceptibility. So I put k equal to 0, and I get m squared. But then there is this integral, this correction, which is divergent, because this correction is 3 lambda over 4 integral ddp over p squared plus m squared. So you have a divergence, and therefore I need to know what kind of, how do I play my interest is in k going to 0. So you're looking at absolutely low energy phenomena. So complete other side of high energy physics. So you are interested in k equal to 0, and you are hit with this divergence over here. All right. So what we found that when I was doing models on a lattice, So we were doing lattice models like Ising in 1D, which is a prototype, or 2D, which we did not complete. The 1D could have been done in very many ways. The 2D is more difficult, and the technique which gets it exactly is quite tough. But all right, the different way of thinking was that I'll go about it piecemeal, which says that, all right, I imagine doing let's focus completely on the 1D case, which we have done in every which way. And so one is more comfortable there. The language, and it remains the same, although the transition here is at t equal to 0, the language remains the same. So what we did was, we said that I will try to connect this, and I'll do the partition function piecemeal, which is do it first over only the, let's say, the even spins, and see what happens. So what will happen is that if I do it over the even spins, the JSI plus 1, the J went to some different J prime, and as you went along doing this, every time I have Jn plus 1, I can write it as a function of Jn, and then we looked for the fixed point of this as f of J star, connected it with the correlation length, and got answers. So that was the RG procedure which we carried out on the lattice. That is, you started getting, the whole idea was that, let's say, if I'm not at criticality exactly, if I am at this slightly away from criticality, the correlation length is very large in terms of lattice constants, and now I make the lattice spacing bigger and bigger by deleting these spins, and until it is just 1 or 2 lattice spacings, and I can now do the. So the philosophy was that go on increasing the lattice spacing, that is, do it over some degrees of freedom which you can control, and then get a recursion relation between the nth step of what you did and the n plus 1th step. This was, yeah. I want to implement this on this field theory. The field theory goes now, has all in this case space, starts right from 0 over here and goes up to some very high number, wave number, lambda, which I'm not so interested in, but it is this 0 where I have to be very careful. So the step 1 over here was, in this lattice, get rid of some degrees of freedom and essentially increase the lattice spacing so that you are, so all right, over here I have a whole range of k's going right up to over there. The point is what I can do is, over here the philosophy would be that integrate, choose some b, choose b greater than 1, and do integration of degrees of freedom. Degrees of freedom means the Fourier modes. So you have a phi of x, which you write as integral dk over 2 pi, let's say phi k, in a d-dimensional space, ddk. D. Yeah. So I choose b greater than 1 and I carry out, do an integration over these. So the degrees of freedom are this k over here, and I do the integration from lambda over b less than k less than lambda. So I want to attack this problem piecemeal. The Gaussian model told me that, and this free energy that I have now is ddp So I want to implement the lattice strategy on the continuum field. The lattice strategy was remove alter, because that's where, I mean, your minimum distance is set by the lattice. You can't, so your minimum distance is set by the lattice spacing. So you have to say, oh, yeah, all right, I mean, let's remove certain set of spins. Now I have a continuum and I have to do an integration over a continuous variable, which is the k. So I'll get rid of some of the small scale business. Over here, I removed, I mean, I made the lattice rarer, so the spacing sort of becomes larger. Over here, I'm going to make the k smaller. So k small is where the action is. And I'm going to make, if you think of this as the lattice, I'm going to get rid of the small part of the lattice, which is the large part of k. Current lattice is x and k is momentum. So small x is large k. And when it's e to the power, Fourier transform, it's e to the power ikx. Small k is equivalent to large x. K and x are sort of inverse of each other. 2 pi by lambda, the wavelength. Yeah. So the small part of, so here we work with, I'm going to implement this scheme with this picture in mind, that I'm going to remove degrees of freedom from this end, from the high k. and see what it does to the parameter which I have over here, which is m square, which is essentially the temperature parameter. So what effect will the removal of degrees of freedom over here have on this particular term over there in the because this is my temperature control. That m square is T minus Tc. That was the whole idea of this Ginzburg-Landau business. And that is the chap which I want to look at. The thing which is a problem for me is this. A standard perturbation theory simply says everything is infinite. Nothing, this is the answer if I integrate overall momentum. So I want to integrate only up to a finite momentum and try to make sense of it. This integral has to probe it has to get to your m equal to 0, which is the low momentum part, which is of importance over here. And this low momentum part, which we will probe by removing the high k part of the action and see what effect it has on the parameters of the problem. This is the philosophy. So the renormalization group, which one did on the lattice, when one does on a field theory, mind you, the high energy, as things started developing through the 80s, the high energy business was exactly the other way around. I mean, they would get rid of degrees of freedom over here and ask what is happening at the high energy end. We will get rid of the degrees of freedom over here in this and ask what is going on in this end. The procedure remains the same. The philosophy remains the same. You are just asking a question about the range in which you are going to focus is different. Good. So, all right. So we'll pick up from here.